Alright, picking up where we left off. If you've watched part 1, you should have noticed that we did a whole lot of vocab and foundational conceptual knowledge and not any practice problems. Like I said, to start that previous video, curve sketching in calculus is contingent. Curve sketching in calculus is contingent upon a very solid foundational conceptual level understanding regarding all the subtle nuances that incorporate graphs. Okay. In algebra 2, it was more so end behavior, x-intercepts, y-intercepts. Then you got to pre-calculus and you started honing in more on the maximum minimum behavior here. We're starting to talk about how is this graph curving, what is the concavity, the inflection points, so on and so forth. If you never heard those words before, that's totally okay. You will get to know them pretty well by the end of this unit. So, picking up where we left off, how do we locate local extrema? Okay. Well, the first thing we can do, like I said at the end of the last video, is the tangent lines at max and min values are horizontal. So that definitely helps out, right? That tells us that f prime of c is equal to 0 at this particular point. And at those points where the function is not differentiable, that's definitely going to be a point of local min or max. And this goes back to our expiration on derivatives when we talked about local linearity. I think middle of the Unit 3 videos, if you want to go back and read through those. But let's introduce a word we're going to use quite often. Critical points. A number C in the domain of F is called a critical point. Okay, remember, domain is a set of x values that makes that function defined. If either f prime of c equals 0, or this is a huge one, f prime of c does not exist. And yes, I know what you're thinking at this point. Can we please do some type of application enough writing? Sure, if you insist. Let's say we have this example. Find the critical points of this cubic. Whoops. I'm already jumping ahead to deriving this bad boy. X cubed minus 9x squared plus 24x minus 10. So, like we said here, right, we need to first derive. So f prime of x equals 3x squared minus 9x plus 24. Derivative constant is 0. If we wanted to, we could factor out a 3, and this becomes a little bit more manageable to derive, except that should be an 18, which makes that a 6. If we were to factor this, right, x minus 4, x minus 2, remember this is the derivative, so we'll set that equal to 0, and we'll see that at x equals 4 and x equals 2, we have critical points. Now at this point, if you're a calculus noob, you might be asking yourself, what do I do at a critical point? Patience. If you're a veteran, slow down. No need to rush. Let's ensure that we have a solid conceptual level of understanding because let's change up the function, right? Let's say we have this function. All right, these examples are also straightforward once we have a nice continuous polynomial. What happens when we change that to the fun ones? Well, the first thing you want to do is definitely remember the behavior of this function. Looks like a v. Notice we have a negative slope from the left hand side towards 0 and then a positive slope moving on. So we're actually going to redefine this to be a piecewise function. It's behaving as x for all x values greater than or equal 0, and it's behaving as negative x for x values less than 0. Once again, we're going to take the derivative. So f prime of x is equal to 1 and negative 1. Once again, for these intervals. And you'll notice our derivatives are constants. But if we're supposed to set the derivative equal to 0, this becomes an impossible conundrum. So we have no solutions such that f prime of c equals 0. Obviously, with x without including x being equal to 0. So therefore, x equals 0 is a critical point. So now that we've done 2 examples, let's talk about the purpose of the critical point. The critical point is like the homing beacon for local extrema. This guy Fermat created this theorem about 3 centuries ago that said if f of c is a local min or max, then c is a critical point of f of x. Furthermore, now let me write this in a different color, right? Because this just tells you the correlation. But what happens if we have a closed interval? So let's assume that f of x is continuous on AB, and let f of c be a minimum or maximum value on AB. Then C is either a critical point or one of the endpoints A, B. Right, so that is something that we definitely want to be cognizant of, that we're including our bounds in our exploration to find where the local maximum and minimum values may exist. And yes, I hear you screaming from the other side of your computer, right, for some practice. So let's find the max and min of this function. Let's have a little bit of fun. 1 minus the cube root of x minus 1 squared on negative 1, 2, closed. First steps first, let's derive this bad boy. Rewrite this so you can do the power rule. So it becomes 1 minus x minus 1 to the 2/3. This will become a 0. This becomes negative 2/3. Right, subtract 1 off of this, so it'd be negative 1/3, so you got a denominator. And then the derivative of the inside is 1, so this is our derivative. And we want to set this, let me do a different color for you visual guys and girls, equal to 0. You should be able to tell that there are no values of x such that the derivative will be equal to 0. But what makes this function undefined? Well, x equals 1. So we must test that point. If we come back to our main function, when we substitute our endpoints, in addition to x equals 1, since our derivative is undefined at that value, when x is 1, f of x is 1. When x is negative 1, f of x is negative 0.59. And when x is 2, f of x is 0. So we can clearly see that we have a maximum value at 1 and a minimum value at 2. Once again, I want to just go back and reiterate this. This is, just computation. Here, since the derivative is undefined at x equals 1, so that c equals 1 is a critical point. That is key. And I'm actually going to sign off, but I'm going to give you one to do without me there to assist you. So find the max and min of one of my favorite functions. Alright, so find the maximum and minimum values of sine of x plus cosine squared of x from 0 to 2 pi. And we're going to talk about that in class.